Hey everyone, and welcome. Think of me as your lab partner today as we jump into this brand new explainer. We're throwing on our virtual lab coats and diving straight into the real core of Class 12 semiconductor practicals. You know, if you've been staring at those textbook diagrams and wondering how these things actually behave when you wire them up, well, you're in the exact right place. We're going to break down some seriously fascinating physics together.
So let's just dive right into it. How exactly do we take all those complex, abstract textbook formulas and translate them into real-world observable measurements right on a lab bench? Because, it's one thing to crunch a number on paper, but it's honestly kind of magic when you see the needle on an ammeter jump or watch a voltage curve flatline exactly when it's supposed to. Today, we're bridging that gap between theory and reality. To pull this off, we're taking a quick tour through 3 distinct lab stations. First up, the foundational PN junction diode. Next, we'll test Zener diode voltage regulation. And finally, we'll verify the logic gates that basically run our digital world. Let's get into it. All right, stepping up to station 1, the PN junction diode. Check out the chemistry that makes this whole thing tick. For the N-type material, when a pure semiconductor like silicon is doped with a pentyl impurity like arsenic, which has 5 valence electrons, 4 of them bond with the silicon, leaving one absolutely crucial free electron. Then, on the flip side with the P-type formation, we add a trivalent impurity like gallium. It only has 3 valence electrons, which means it physically can't complete the atomic bond with the surrounding silicon. That leaves behind an incomplete bond, or what we call a hole. These free electrons and holes, they are the literal charge carriers that make the magic happen when you stick these two materials together. Now, what happens when we actually apply power to that junction? Well, the VI, or voltage current characteristic curve, tells the whole story. When we forward bias the diode by connecting the P-type to the positive terminal and N-type to the negative, the current starts out incredibly tiny. But as that voltage increases, suddenly it hits a very specific point and the current just shoots straight up. Now, conversely, in reverse bias, that current is practically zero until it gets pushed all the way to its breakdown voltage. So, you know that really sharp upward turn we just saw? We call that the cut-in voltage. It's the absolute minimum bias voltage you have to apply across a diode for rapid conduction to kick in. Below that threshold, current is essentially blocked. Above it, the floodgates open. In your actual lab observations for a standard silicon diode, this threshold sits right around 0.6 volts. For germanium, it's about 0.2 volts. Finding that exact knee in the curve is basically your main mission at this lab station. Moving right along to station 2, Zener diode voltage regulation. Now, unlike your everyday diodes that would probably fry in reverse breakdown, the Zener diode is heavily doped and literally designed to thrive there. To prove the Zener acts as a true voltage regulator, meaning it keeps DC voltage perfectly stable no matter what, we break the experiment into 2 steps. First is line regulation, where we vary the input voltage but keep the load constant. Second is load regulation, where we freeze that input voltage but vary the load resistance. Okay, setting up our first circuit for line regulation. Notice the architecture we're working with. We've got our Zener diode connected in reverse bias. The load resistance, RL, is kept totally locked in at 2 kiloohms. But the input power supply, we actively mess with that. We adjust the input voltage, dialing it all the way up to 35 volts, just to see if the Zener can handle the pressure and keep the output completely steady. And boom, here is the payoff. When we plot this out, our supply voltage is soaring from 0 up to 35 volts. But look at the output voltage. It rises at first, sure, but the second it hits the Zener breakdown point, it beautifully flatlines, locking in right around 5.1 volts. The input voltage is doubling, tripling, just surging higher, and the Zener diode, it completely ignores it, delivering a perfectly regulated 5.1 volt output to the load. Pretty awesome, right? Switch gears for a second to our load regulation setup. This time, it's the exact opposite approach. We freeze the input voltage source at a constant 20 volts. But now, we actively adjust the load. We're twisting the dial on a rheostat, changing the load resistance just to see if the Zener can maintain that output voltage, even when the demand from the load is constantly fluctuating. Analyzing the results here, we see that as the load resistance drops, the Zener seamlessly maintains a constant output near 5 volts. Well, up to a point. Once the load resistance drops a bit too low, below a specific minimum value, the regulation completely drops off. But this perfectly proves the concept. The Zener diode is an absolute powerhouse as a voltage regulator, as long as you keep that load resistance above its minimum threshold. Let's step into our third and final lab station, verifying logic gates. We're totally leaving the analog world of fluctuating voltages behind and jumping straight into the crisp, zero-tolerance digital realm of binary logic. These gates are the literal building blocks of every digital system. They process binary inputs, just ones and zeros, highs and lows, and spit out a single binary output based on a hard set of rules. We're talking the primary gates like AND, OR, and NOT, then the universal gates, NAND and NOR, and of course the exclusive gates, XOR and XNOR. Let's compare a couple of the foundational rules you'll be wiring up on the breadboard. The AND gate has incredibly strict logic. It is an all or nothing deal. It will only give you a high output, a logic 1, if literally all of its inputs are high. Contrast that with a much more laid-back OR gate. It's perfectly happy to give a high output if just one or more of its inputs are high. These simple conditions are exactly what we test using basic transistor or diode logic circuits.
To actually verify these, we rely on truth tables pulled straight from the lab manual, like the ones for the 7402 NOR gate and the 7486 XOR gate. The XOR gate is kind of fascinating. The output is a 1 times only when the inputs A and B are different, like a 0 and a 1. If they are exactly the same, both zeros or both ones, the output is strictly a 0. You verify this right there on the lab bench by toggling the input pins and watching the output LED light up, following these rules to the letter.
And that wraps up our virtual lab tour, but I want to leave you with something to chew on. Today, we looked at just one single PN junction, one Zener diode regulating a few volts, and a truth table checking just 2 inputs. How do these microscopic, fundamental rules of physics scale up millions and billions of times over to create the very screen, the processor, and the memory of the device you are using to watch this explainer right now? Because I promise you, the whole shebang starts right here on the lab bench. Keep questioning, keep experimenting, and I'll catch you in the next explainer.